The wye-delta transform, also written wye-delta and also known by many other names, is a mathematical technique to simplify the analysis of an electrical network. The name derives from the shapes of the circuit diagrams, which look respectively like the letter Y and the Greek capital letter delta. This circuit transformation theory was published by Arthur Edwin Kennelly in 1899. It is widely used in analysis of three-phase electric power circuits. The wye-delta transform can be considered a special case of the star mesh transform for three resistors. In mathematics, the wye-delta transform plays an important role in theory of circular planar graphs. Names. The wye-delta transform is known by a variety of other names, mostly based upon the two shapes involved, listed in either order. The Y, spelled out as Y, can also be called T or star. The delta, spelled out as delta, can also be called triangle, pi, or mesh. Thus, common names for the transformation include wye-delta or delta Y, star delta, star mesh, or T-pi. Basic wye-delta transformation. The transformation is used to establish equivalence for networks with three terminals, where three elements terminate at a common node and none are sources. The node is eliminated by transforming the impedances. For equivalence, the impedance between any pair of terminals must be the same for both networks. The equations given here are valid for complex as well as real impedances. Equations for the transformation from delta to Y. The general idea is to compute the impedance at a terminal node of the Y circuit with impedances to adjacent nodes in the delta circuit by where all impedances in the delta circuit. This yields the specific formulae equations for the transformation from Y to delta. The general idea is to compute an impedance in the delta circuit by where is the sum of the products of all pairs of impedances in the Y circuit, and is the impedance of the node in the Y circuit which is opposite the edge. With the formula for the individual edges are thus circuit analysis. Techniques for solving delta to Y. A circuit that has a combination of delta loads and Y loads should be converted to the Y configuration. By converting from delta to Y, each circuit element can be analyzed separately. Converting from delta to Y is a technique aimed to simplify circuit analysis. The conversion from the delta notation to Y notation is as follows. A proof of the existence and uniqueness of the transformation. The feasibility of the transformation can be shown as a consequence of the superposition theorem for electric circuits. A short proof, rather than one derived as a corollary of the more general star mesh transform, can be given as follows. The equivalence lies in the statement that for any external voltages applying at the three nodes, the corresponding currents are exactly the same for both the Y and delta circuit, and vice versa. In this proof, we start with given external currents at the nodes. According to the superposition theorem, the voltages can be obtained by studying the linear summation of the resulting voltages at the nodes of the following three problems applied at the three nodes with current, and it can be readily shown by Kirchhoff's circuit laws that one notes that now each problem is relatively simple, since it involves only one single ideal current source. To obtain exactly the same outcome voltages at the nodes for each problem, the equivalent resistances in the two circuits must be the same. This can be easily found by using the basic rules of series and parallel circuits. Though usually 6 equations are more than enough to express 3 variables. Here it is straightforward to show that these equations indeed led to the above designed expressions. In fact, the superposition theorem not only establishes the relation between the values of the resistances, but also guarantees the uniqueness of such solution. Simplification of networks. Resistive networks between two terminals can theoretically be simplified to a single equivalent resistor. Series and parallel transforms are basic tools for doing so, but for complex networks such as the bridge illustrated here, they do not suffice. The wye-delta transform can be used to eliminate one node at a time and produce a network that can be further simplified, as shown. The reverse transformation, delta y, which adds a node, is often handy to pave the way for further simplification as well. Every two-terminal network represented by a planar graph can be reduced to a single equivalent resistor by a sequence of series, parallel, wye-delta, and delta y transformations. However, there are non-planar networks that cannot be simplified using these transformations, such as a regular square grid wrapped around a torus, or any member of the Peterson family. Grawr theory. In Grawr theory, the wye-delta transform means replacing a y subgraph of a graph with the equivalent delta subgraph. The transform preserves the number of edges in a graph but not the number of vertices or the number of cycles. Two graphs are said to be wye-delta equivalent if one can be obtained from the other by a series of wye-delta transforms in either direction. For example, the Peterson family is a wye-delta equivalence class. Demonstration. Delta load to Y load transformation equations to relate from delta to from Y. The impedance between two corresponding nodes is compared. The impedance in either configuration is determined as if one of the nodes is disconnected from the circuit. The impedance between N1 and N2 with N3 disconnected in delta. To simplify, let B the sum of. Thus, the corresponding impedance between N1 and N2 in Y is simple. Hence, repeating 4 and 4. From here, the values of can be determined by linear combination. For example, adding and then subtracting yields. Thus, where for completeness, Y load to delta load transformation equations let. We can write the delta to Y equations as multiplying the pairs of equations yields, and the sum of these equations is factor from the right side, leaving in the numerator, cancelling with an in the denominator. Note the similarity between imp divide by, which is the equation for dividing by, or gives the remaining equations.